Assalamualaikum warahmatullahi wabarakatuh to my panels and fellow friends. Today I will be presenting my final year project entitled Antimicrobial Activity of Biodegraded Amoxicillin by Aspergillus tamarii against Escherichia coli and Staphylococcus aureus. Global antibiotic consumption surged by 65% from 2000 to 2015, and excessive use and improper disposal pose environmental threats by promoting antibiotic-resistant microorganisms, though various methods for eliminating antibiotics exist, including the use of filamentous fungi which produce enzymes capable of degrading antibiotics. Therefore, the problem statement of this study is that amoxicillin is a complex and slow to degrade structure which will contribute to antibiotic contamination and antimicrobial resistance. But unfortunately, the current methods used to address antibiotic contamination are often not environmentally friendly. The research questions of this study are: what is the antimicrobial activity of biodegraded amoxicillin samples against E. coli and S. aureus? And also, what are the differences in biomass yield and growth rate of Aspergillus tamarii with amoxicillin and without amoxicillin during batch fermentation? Therefore, the objectives of this study are to evaluate the antimicrobial activity of biodegraded amoxicillin samples against E. coli and S. aureus, and also to observe the differences in biomass growth rate of Aspergillus tamarii with amoxicillin and without amoxicillin during batch fermentation. Thus, the significance of study are to understand the effect of antibiotic degradation by Aspergillus tamarii, particularly its antimicrobial effects against specific bacteria, and also to examine the differences in effects between degraded and non-degraded antibiotics, offering insights into the biodegradation process using fungal biomass. Antibiotic degradation using filamentous fungi is considered an eco-friendly and sustainable alternative. Beta-lactamase of Aspergillus tamarii can break down amoxicillin into amoxicillin acid by opening the beta-lactam ring. Aspergillus species produce tannins, which significantly improves ester bone hydrolysis and alters the structure of amoxicillin to make it less harmful to the environment. This is the flowchart of methodology. The morphology of fungi was observed after 3 days and 7 days of incubation at 27 degrees Celsius, which is a rapid growth rate for Aspergillus tamarii. The colony characteristics form interval matcha dark and light green color stripes on inner sides, and white color was noted at the colony's edge. It also shows a woolly or cottony texture. The microscopic examination by observing the edge colony, it shows the unbranched conidiophores with long, smooth ends which end in a round vesicle. The shapes of conidio are round with form in chains, and the hyphae are septate and hyaline. Next, to identify the bacterial species, I conducted 3 methods, which are gram staining, strict plate method, and biochemical tests such as catalyst tests. The gram staining experiments identified that E. coli have pink colored colonies, which indicate that E. coli is gram negative, while S. aureus have purple colored colonies, which indicate gram positive bacteria. After I stripped the stock culture on MHA, E. coli shows a smooth, round and moist appearance with off-white color and creamy texture. For S. aureus, shows round, smooth and slightly raised with yellow to white color and buttery texture. Lastly, both of these selected bacteria indicate that catalyst positive since they have the formations of bubbles. To achieve my first objective of this study, antimicrobial activity was conducted to verify the biodegradation of amoxicillin against E. coli and S. aureus. These 2 bacteria were used because they are susceptible to amoxicillin, thus to test the resistance of biodegraded amoxicillin. The picture shows that there are differences in the inhibition zone of amoxicillin standard solution, abiotic, and biodegraded amoxicillin biotic. These results show that Aspergillus tamarii can break down amoxicillin effectively. For the growth curve, it determines the effect of amoxicillin when added after 96 hours. The graph shows the decrease of a fungal biomass after amoxicillin was added. Therefore, it can be ascribed to the significant decrease in amoxicillin activity observed in the selected bacteria. Next, to achieve my second objective is by comparing the differences of dried weight fungal biomass between biotic and abiotic samples from 24 hours to 168 hours. Both samples show initial growth within the first 24 hours. Then after 48 hours, the abiotic sample shows a more significant increase in biomass compared to biotic sample. It shows the presence of amoxicillin in biotic sample seems to have an inhibitory effect on the growth of Aspergillus tamarii, which is leading to a lower biomass compared to the abiotic sample that without amoxicillin. The initial rapid growth in the abiotic sample suggests that without the inhibitory effects of amoxicillin, the fungi can proliferate more quickly. Both samples eventually reach a stable phase, but the abiotic sample maintains a higher biomass throughout the observed period. Lastly, to support my data, I conducted statistical analysis by using one-way ANOVA. This graph shows the average of dry fungal biomass between biotic and abiotic samples from 24 hours to 168 hours. This shows that there are a significant difference in the mean concentration of amoxicillin over the 7 time points studied. The p-value is 0.000, which is less than the significance level, which is set at 0.05. The conclusion of this study, the biodegraded amoxicillin samples show reduced antimicrobial activity against E. coli and aureus. This indicates that Aspergillus tamarii can degrade amoxicillin. This also suggests that the biodegradation process diminishes the antibiotics' effectiveness, highlighting potential challenges in managing antibiotic residues in the environment. It also demonstrated that amoxicillin inhibits the growth of Aspergillus tamarii, leading to lower biomass yields in biotic samples compared to abiotic samples. This was evidenced by the differences in the dried weight observed in the growth curves. Lastly, for future recommendations of this study, I would like to utilize high-performance liquid chromatography (HPLC) to quantify the concentration of amoxicillin and its degradation products over time. This method will provide accurate measurements and help in determining the rate and extent of degradation of Aspergillus tamarii. Also, I will suggest to conduct growth inhibition assays to study the antimicrobial activity of biodegraded amoxicillin samples by using standard strains of bacteria and measure their growth inhibition at 24-hour intervals. That's all from me. Thank you.